Okay, this is lesson 11 of module 3, more about similar triangles. In this lesson, we are going to put together some of the things we already know about dilations and the fundamental theorem of similarity, the angle-angle criterion that we talked about in lesson 10. And we're going to be looking at triangles and with given information, trying to figure out whether they are similar or not. So this is a really important thing that you'll be doing in geometry and that you're doing now in geometry. And in lesson 12, we'll see applications of similar triangles in real world problems. So we're coming to the end of this module, and it seems like people are really kind of putting this together now. So that's good to see. Okay, so let's look at some examples. Okay, so in this first example, this is example 1. We have triangle ABC and triangle DEF, and the question is ABC similar to DEF? So is triangle ABC similar to triangle DEF? So notice what we're given. We're given a corresponding angle that is equal in measure, and we're given the lengths of two sides of each triangle. And so I want you to pause the video and think, am I able to tell if these two triangles are similar? So we knew from the last lesson that if we had two angles, two pairs of angles that were equal in measure in two different triangles, that we could know they were similar. So so think about this one, and then we'll go on and talk about it. All right, so let's look at this. We only have one angle, so we can't use the angle-angle criterion to determine if these two triangles are similar. So we're going to have to do something else, and we're going to use the fact that those side lengths appear to be proportional to do this. So what I'm going to do is we're going to think if we translated this triangle DEF to where the two matching angles coincide, and I'm going to just mark where point D, approximately where point D and F would be right in here somewhere. So we would have a triangle right here. That would be DEF. So we could label E right here and F down here. So we've got triangle DEF, and A and D are now the same point right up here. Okay, so we got A and D and E and F. So we've put them in this place, and so it might not be immediately obvious why these lie on the same line, but if you think about the fact that those angles match, E and F will have to lie on the sides of that triangle because of that 39-degree angle. Okay, so let's look at this. So we have length DE. So length DE. Whoops, sorry about that. Length DE is equal to 1. Length AB is equal to 2. And length DF is equal to 3. And AC is equal to 6. So those are all lengths we're going to need. So if we could show that line EF right here, this line, is parallel to this line, then we could know that this angle here, DEF, is congruent to angle ABC. Okay, so if we knew these two lines were parallel, well, the only way these two lines could be parallel is if E and F were the dilated points of B and C. So E would have to be the dilation of B, and F would have to be the dilation of C by some common scale factor. And if that's true, then the fundamental theorem of similarity says that these lines here will be parallel. These two lines will be parallel, and then I can know that the corresponding angles are equal, because I would have parallel lines cut by a transversal and then cut by this transversal. Okay, so let's see how we would figure that. So I would want, if point E here is going to be the dilation of B, then I would need to look at the ratio of, the dilated ratio would be A E, or DE, better call it DE. Call it DE over A B, and that value is 1 over 2. We would need that to be the same as, so that would be the scale factor of the dilation along AB. So then we could look at the other side here, AC, and so we'd have the dilated length would be DF or AF, and the original length would be AC. Okay, so DF is 3 and AC is 6. So that also is equal to 1/2. So what we have here is a dilation. So we have a dilation from center A, and we know that the dilation of B is E, and the dilation of C is F by a scale factor of 1/2. So the fundamental theorem of similarity that we looked at starting in lesson 4 tells me then that I have parallel lines. So that means that line EF joining the dilated points is parallel to BC, the line segment joining the original points. Okay, so if these triangles are, or if these lines are parallel, then I know that this angle and that angle are the same, and that angle and that angle are the same. So now I have all three angles of these triangles equal, and therefore the triangles are similar. So the answer to the question is yes, they're similar. So we've learned another way besides angle to tell if two triangles are similar, and that would be having one angle and having one pair of corresponding, or two pair of corresponding sides in ratio according to a common scale factor. Okay, so let's look at another one. Okay, so here's the diagram for our next example. So in this one, once again, we're asked, is triangle ABC similar to triangle A, B prime, C prime? Okay, so here's point B, and here is B prime. Here's C, and C prime, and here's point A. So we're given the triangle is, the smaller one is already superimposed. So we do have the one angle. So what we want to check for, based on this last example, is we want to see if these two lines are parallel. If they are parallel, then I know I have these angle congruencies. Okay, but I bet you're saying, but they're not parallel, because look at them. They're not parallel. They don't look parallel, but I have to go by, remember, what is explicitly told to me on a diagram. So I don't know if those are parallel until I've checked a few things, because they haven't told me they are and they haven't told me they aren't. So I'm going to check the ratios. So I'm going to check for a common scale factor of the dilation of B to the scale factor used to dilate C. If it's the same scale factor along both of those sides, then I know I have a dilation, therefore I have parallel lines and I have similar triangles. Okay, so let's check. We're going to check. So these are the dilations, the primes. So we're going to check AB prime compared to AB. So the length of AB prime divided by the length of AB is going to give me the scale factor that was used to dilate that point. Okay, so this would be 8. Is it just 8 there? Yeah, sorry. It is 8. Okay, so we've got 8 over 4.9. And then for this other ratio that we're going to check, we're going to do AC prime over AC. So this is 7.1 divided by 2.7. So when you do the division on these two fractions, you can see that the scale factor used to dilate B was 1.6 and to dilate C was 2.6. So therefore, B prime, C prime is not parallel to BC, the original segment. So we don't have parallel lines, therefore we don't have congruent angles. So ABC is not similar to A prime, B prime, C prime. Okay, this next example is a little bit different. This next example tells us that we have similar triangles. Triangle ABC is similar to triangle A, B prime, C prime. So let me label this so you can see it a little better. So there's B prime and C prime. There's point C, point B, and A. Okay, and we're also given some lengths. We're told that AC is 5, AC prime is 15, and AB is 2. So it says, how could we determine the length of AB prime? So that's this longer length here that I'm not given. What does it mean to say that triangle ABC is similar to AB prime, C prime? So in order for these two triangles to be similar, we need to have all the angles would be equal. So we'd have all congruent angles. Okay, and we'd have all corresponding sides in proportion. So that would mean that AC prime over AC is equal to AB prime over AB. And it would mean that BC, B prime, C prime over BC is also equal. So they're all in proportion by some scale factor because this is, these are similar triangles, okay? I also know that these two lines here are parallel because they're similar triangles. Okay, so we're going to use this right here to help us with the finding the missing length. AB prime is what I want to find out. So let's look at which of these ratios do we know. Well, we know AC and AC prime. So we don't know AB prime yet, and BC prime and BC aren't labeled. So we can come over here and say that AC prime over AC is 15 over 5, which is 3. So it's a scale factor of 3 that the smaller triangle's been dilated by. And so I can come over here to this side and dilate it by a scale factor of 3 to find out where B prime is. Because I've been told that these are similar triangles. That's the only reason I can do this. So AB prime is equal to the scale factor R times, and let's just go ahead and put what it is in. Scale factor is 3 times the original length, AB. So AB prime is equal to 3 times 2, which is equal to 6. So this length here, this whole length here is 6, because the scale factor is 3, and I know what I know about similar triangles. Okay, another one. Okay, in this next example, here's our diagram. We are told that segment XY and X prime, Y prime are parallel. And we're asked, is triangle OXY similar to triangle OX prime, Y prime? So we know because of the similarity, of course, we have a matching angle there. We have a matching angle here and another one over here. So we have angle, 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 so we know that those would be similar. We could also find out some missing lengths using the scale factor. Can we find, so we want to find the length OX prime and the length OY prime. So first we need to know what the scale factor is. So scale factor, remember, is always the dilated length over the original length. Okay, and so the only pair of corresponding sides that I have to work with would be these. So my scale factor is 6.25 divided by 5, which simplifies to 1.25. Okay, so now I want to use this scale factor to find those missing lengths. So OX prime would be the scale factor times length OX, which is 4. 1.25 times 4 is 5 units. And then OY prime is 1.25 times the length of OY, which is 6. And 6 times 1.25 is equal to 7.5 units. Okay, so we have found both lengths there using the ratios of the side lengths using what we know about scale factor. Okay, in this next example, we are asked to determine if OPQ is similar to OP prime Q prime. And so we're given some things on this diagram and asked to explain. Okay, so we know they have one angle in common. They have this angle up top, angle O, we'll call it, in common, but they don't have two angles. So we can't use angle criterion. If we knew that P prime Q prime was parallel to PQ, then we would have corresponding angles equal and we would have similar triangles. So we would need to check for to see if this is a dilation, to see if P prime is dilated from P. But we can't check for that because we're not given any lengths on the original triangle. Therefore, we can't tell if these two are similar. We would need to know length OP and length OQ in order to check to see if these are similar triangles. Okay, so now we're going to look at the exercises in your notes. So I'll be doing that on a separate video so that, because these were all covered in class. So look for part 2 of lesson 11 to find the exercises done.